Hi, my name is Baron Schwartz, and I'm the CEO and founder of VividCortex. And today I'm going to demonstrate how you can use a spreadsheet to model system scalability with the Universal Scalability Law. The spreadsheet is downloadable from the VividCortex website, and I'm just going to demonstrate how you can use that. So let's go right ahead and get started. First of all, here's what we're going to cover in this brief tutorial: an introduction to the Universal Scalability Law, and then a tutorial to how to actually use this spreadsheet that I've created. So let's look at what the USL is. It models why systems don't scale linearly when you add size or load to them. And when people think of linear scalability, this is often really what they're talking about. Systems don't scale linearly because there are increasing costs of operation, costs of overhead as the systems scale, and those begin to penalize the amount of work that the system can do. The Universal Scalability Law is a function that models that, and you can feed it with some relatively easy to get data. In fact, that's data that VividCortex and many other types of systems capture. And you can use the Universal Scalability Law to determine, first of all, the scalability limits of your system, so you can project the model out beyond the observed data to figure out how much runway you have before your system starts to struggle. And secondly, you can understand why your system doesn't scale linearly as it should. You can understand whether which of the two factors at play is really dominating, and therefore what you can do to make it scale better. So what is linear scalability? Ideally, as you scale a system up, either adding load or adding capacity to it, you get sort of a linear relationship between that scaling and the results that you get from the system. So results meaning the work that the system does. So for example, as you add nodes to a clustered system, if you double the number of nodes in the system, you hope that you can do twice as much work, twice as many queries per second, whatever your system is doing, with the doubled size of the system. In reality, that usually doesn't happen. So ideally, the scaling function is a straight line going through the origin and extending out horizontally up and to the right. In reality, what often happens is that those performance metrics that you get from a system will actually drop below that diagonal line as you scale. And there is a mathematical function, that's the USL, that expresses this relationship and why systems don't scale well and what those factors are. So the key components of this are the load that you place on the system. Usually that's something like concurrency, or the number of threads running in the system, or the number of workers in the system, like those nodes in that clustered database. And the amount of work that you get done, which is throughput. That's completed queries per time. The USL itself is not a terribly complicated equation. On the left-hand side of the equal sign, it's throughput for a given size or load, that's n. And on the right-hand side, you've got a couple of parameters. The important ones are in the denominator. There's sigma, which is the coefficient of serialization. That expresses how much queuing delay your system experiences. And then there's kappa, which is how much crosstalk, that is the shared coherency of data that needs to be communicated between systems, or other kinds of cross-node or cross-worker unit synchronization. And so if you use regressions, fairly straightforward to estimate the size of those parameters, sigma and kappa, and then you can model your system and see how it's going to scale. See how it should be scaling, and see what you can do to make it scale better. So the data that you can plug into this is fairly straightforward, as I said. In VividCortex, for example, these metrics come in a variety of shapes and sizes. And in some cases, you might have to understand the meaning of the metric a little bit to know that it's a valid input to this model. For example, in the metrics that we accumulate by sniffing from the network, we accumulate both very granular metrics as well as overall totals for a host or a database server. And one of those is the total time accumulated in microseconds for a database server, and another one is the throughput in units of time. And in this first system here, there's two systems shown on this slide. Notice that we have a decent amount of variability. So this system is going up and down through some peaks and troughs. And you really want that to get a good set of data input into your model. If you basically give it a whole bunch of metrics of the same thing, if those were flat lines, then you wouldn't have enough points to extrapolate and model with. On the bottom, we have a system that's not quite as easily modeled. The first metric, the threads running, actually has a decent amount of variability in it, although not as much as I would like to see to be really indicative. And then the next couple of metrics are more flat lines. There's not very much variability in them. I included the second one because I wanted to show that for MySQL in particular, there are some of the metrics you can get right out of MySQL that are valid inputs to this model. Threads running is essentially a metric of concurrency. Here we have the same metric again, time in microseconds, so that's total accumulated time, which by Little's law is equivalent to concurrency. And you can see those first two charts here are not the same shape, so they're really measuring slightly different things. So garbage in, garbage out, you got to know where your data comes from. And then the final one is the MySQL status counter for queries, which is a metric of throughput. Okay, so that's all of the slides. Let me get rid of this slideshow and bring up the spreadsheet that I've created. So here's our spreadsheet, and there are two tabs on this. The first one gives you a space to put in your metrics, and you can put in 1,000 rows of data. I'm starting out here with just a fairly small amount of data. So you have two columns, one of concurrency and one of throughput. So this is the load or size or load or size of the system, and the second one is the throughput, the queries per second that you can get out of it. And so we've only got 10 rows or so. When we switch to the analysis tab, everything on the bottom here, you can ignore all of this stuff. This is all carried over from the first tab, and there's some derived calculations that we need to do the modeling. These feed into various things, and then the cells in green are ones that you can, parameters that you can change if necessary, because the model sometimes requires a little bit of adjustment, and we'll see a couple of cases where that is true. So with these 10 data points from the first tab, you can see those plotted here in the large chart, and they're plotted with concurrency on the x-axis and throughput on the y-axis, and then each of these little points is a little circle here. Those may be a little bit faint. You'll see later why those are faint. They're partly transparent, and that's important for this spreadsheet itself to scale to large amounts of data. And then we do a regression. The regression actually happens on some transformed data up here, and you can see the parameters coming out of that. This is essentially transformed into how much nonlinearity is there, and it's the nonlinearity that becomes an accumulating cost as the system grows. And then we basically down here, we subtract that from the straight line, and we get this curved line, which in fact actually goes down over time. It doesn't just flatten off, but you can get retrograde scalability as well, and that's not uncommon to see in systems. If you keep an eye out for benchmarks that you see in the future, you will notice that they're often pushed beyond their saturation point, and they start to give you retrograde scalability. Crosstalk accounts for retrograde scalability, and queuing delay accounts for just flattening off and kind of reaching an asymptote where you don't get any more bang for your buck as you scale the system. So the dotted line is essentially, that's the model, and we can project it out. I have this spreadsheet calculating how far out this point is, the furthest rightmost point, and then projecting twice as far out beyond that, so that you can see, if you pushed this system to a concurrency of, this point is at concurrency 20, but if you pushed it to a concurrency of 40, you can see it would be past its peak if this model is correct. All right. So this data is relatively nice and clean. Let's look at a couple of different data sets. So I've got another spreadsheet off screen here that I'm going to copy and paste some stuff from. Let's look at a different data set where hang on, I can't talk and type at the same time. And Excel uncopied what I had. So let me switch back and paste that in again. Okay, there we go. So this is a different system that was measured under a benchmark with increasing amounts of load. And it's nice and clean. It's cleaner than the first system that we looked at, and the model is quite accurate. In fact, even if we did our modeling on a subset of this data up until here, the model would project out the rest of the results fairly accurately. There's some interesting effects here. It kind of wiggles around a little bit, and those relate to the hardware, the underlying hardware. So this is a hardware benchmark of a Cisco server. So it's in a very pure kind of a laboratory environment. This is kind of the frictionless plane scenario with spherical cows skating around on it in all directions. So this is a nice clean system. You can see how well this model works in that scenario. Let's look at a larger set of data. And this comes from VividCortex from a much larger time range on a Postgres database. And let me go back here and paste it in. And there are, I think there's several hundred rows of data here. Yeah, so there's 263 rows of data here in this system. And now you can see why I have partially transparent blue circles, because when you get a few hundred rows of data, they start to obscure each other, but you can see by the darkness of those overlapping rows, you can kind of see where the data points are clustered. So let's look at this system. If you kind of ignore the dotted line extending out to the right here, and you just look at where this kind of hairball of blue dots is on the screen, look at the general shape of this. As this system scales, if the bulk of the data points, the measurements are around in this area, if it scaled linearly, then as we loaded it up into the concurrency of 10 things at a time and 15 things at a time, the throughput would really be up in this area. But it isn't. It is falling off. You know, at these higher concurrencies, at concurrencies of 15 or 20, we see it start to fall off and we get a decreasing return on investment. So although the modeled curve in the dotted line actually matches this not too badly, R squared of 0.73, which is not too shabby. I mean, it's not phenomenal, but it's not too shabby. Although it matches that well enough, even so, even without that, I would be able to tell you from my experience with performance modeling that as we start to see these outlying points here, the system is starting to struggle, because you can see a very clear trend of it really can't, you know, at higher concurrencies, it really can't break through a throughput of 600 queries per second or so. So this system is not going to scale much beyond, you know, around this point here. And what's going to happen is you push the system beyond that saturation point, which is probably related to the underlying hardware, you're going to see increasingly poor quality of service. You're going to see erratic response times and stalls and, you know, just dramatically poor, inconsistent behavior. So probably, I don't know the underlying hardware of this system. I'm not privy to that. But what I would guess is that probably the system has 8 CPUs, and you know, you're not going to be able to run more than 8 queries at a time on 8 CPUs. You can do it, but some of them are going to have to get in line and wait. And so anywhere beyond 8 CPUs, the system is inevitably going to encounter a lot of queuing delay. So, saturation in action. Let's look at another one from a MongoDB database. And go back and paste this data in. I keep uncopying accidentally. Sorry about that. Okay. So back to the analysis tab. This one has about the same number of rows of data, 263. I pulled it off of the same chart. I actually pulled this out of an API call. So I pulled the JSON out and transformed it into CSV data. A couple of things to notice. Whereas before the system was saturating and you were getting retrograde contention and retrograde scalability, this system is actually scaling smoother. It's a little bit cleaner. It's struggling a little bit less. Notice that the x-axis is not extended so far. So this system is running at relatively lower concurrencies, so that you know, it's not getting into trouble. And yet you can still see that the model is basically right. The system is not linear. It is starting to fall off up here in the upper ranges. And so I would guess that we probably can't scale this system beyond about twice its current load. And at that level, you know, we would probably expect it to achieve a throughput of 1,600 queries per second or something like that. So you can really start to get a sense for how much runway, how much headroom does the system have. Okay, so let's empty that out again, and I'll go find another data set. And now we're getting to a MySQL server. I'm not doing these in any particular order for any particular reason. It's just how they happen to happen. And this one is a little bit harder to interpret. It's like, what is going on here? And in fact, the model starts to struggle a little bit. We've got some divisions by zero. We've got some things going negative, negative coefficients in the regression up here. So this system is a little harder to interpret. Not every system is nice and clean. It doesn't always work out magically. And so that's just a general thing. You know, sometimes this model's going to be good and you're going to get good results out, and sometimes you're going to go, well, you know what? I can't really draw any conclusions from this. Another one also from a MySQL server. I just wanted to show you a variety of things here. This one's a little bit noisier because the points are kind of scattered around a little bit more. You can see that there's some outlying points here that don't have very good throughput. So as the system gets into the little bit higher concurrencies here of 4, 5, 6, these points for whatever reason are not super clean. Doesn't look like we have very many of those points, but it might be something to be aware of, just sort of a cautionary tale. Now when I look at this system, I see the hairball up here, kind of the fan out. There's a nice tight cluster down towards the lower end and a little bit of a hairball and a fan out dispersion towards the higher end of that clump of points. When I look at that, I think the system is getting less consistent and less predictable at those upper ranges. So this one I do know, this is one of VividCortex's own servers, and I do know this one's running on a small EC2 instance with 2 virtual CPUs. So I'm not surprised to see that it doesn't really do very well on the higher end there. And there's a few others that I wanted to show you, just to give a sense of the variety of data that we get with this. I pasted over my column headers there accidentally. This one's interesting. So there's a very tight cluster, and it does not point at the origin. If you kind of visually draw a line through this, it doesn't point at the origin, it points at 5. And the model freaks out. It doesn't know what to make of this. So this is where the parameters that you can manipulate come into use. Now, oftentimes the concurrency might be artificially inflated by something that is counting towards concurrency but doesn't really do any productive work. So systems that do this, for example, might have a concurrency counter that gets influenced by something like a replication thread that always appears to be running but isn't really doing any work on the host system and doesn't count towards the same kind of work set that the rest of it does. So there's an n offset parameter up here in green that we can manipulate to account for this. So as we increase that from 1 to 2, you can see how the model adjusts to accommodate for that. And really it looks like the right answer is around 4 or 5. So perhaps 4 is the right answer, and we're just shifting the whole thing to the right. Maybe 5, but I think the model is, yeah, maybe it is around 5. So you can see that sometimes you need to do things like clean up your data or make a compensation for skew or other kinds of distortion in your data set. And sometimes you might also need to do things like resample, downsample, smooth your data, get rid of outlying data sets, but that's kind of beyond the scope of this little tutorial. Now another thing, the model needs to know what linearity looks like, and for that it really needs to know what throughput of 1 looks like, and that's this C of 1 parameter here, which in this case is about 46 or 4700 queries per second at a concurrency of 1. If C of 1 is given in the data set, this model will use what's given there. If it's not, then it will estimate it, and this is one of the influential kind of portions of this. We estimate it by looking at the lower percentiles of the data set. So we could, for example, estimate it by looking at the lower 5% of the data set. We could look at the lower 50% of the data set. And so the model uses that to feed in. By default, I leave it set at around 15%. This data set is quite dense and quite uniform in the lower ranges there, so it doesn't really appear to make much difference. There's a few other things that we can do just to tweak some of the parameters. For example, if we think that it's underestimating that value of capacity of 1, then we could add, for example, another 20% to it, and you'll see how the model changes for that. And just to illustrate, sometimes the model actually says that the contention or crosstalk parameters are negative, and those are sort of unphysical, or not totally unphysical, but a little bit beyond the scope of this. But let's say that we thought that 47% of coherency of a queuing delay was a little much, which I think it is a little much. This is a very badly scaling system. We could subtract, for example, 10% from that. And whoops, I subtracted far more than 10% from that. Negative 10%. And you can see how the model adapts to that. This parameter here, the one that I've just highlighted in cell C9, is actually the input to the model, and the green parameter here is kind of an override or a manual adjustment to that. All right, and if you do want to see what happens with negatives, you can change this parameter to 1 and let the model work itself out. Here it doesn't estimate that any of the parameters are negative, but in some of the previous ones it would have estimated a negative in one of those parameters. There's lots more that we could do with this. I just want one final note, and then I'm going to drop off and leave you. The data that I got from this is relatively easy to get as JSON just by getting for example, you can load up the VividCortex web app, and you can right-click and use the Chrome inspector and look at the network requests that it makes. Click on one of those and copy the JSON response, and then you can use convertcsv.com to get something that's really easy and ready to copy and paste into a spreadsheet, and then you just use paste special with transpose to get it into the column shape that you need for the inputs on the first tab of this spreadsheet. So quite easy to get all of this data. It's readily available, and hope you have fun modeling your systems. If you want to try this out for yourself, go to vividcortex.com, and under the Resources tab, you will find this spreadsheet ready for download. You'll also find an ebook that I wrote, which I think is probably the most comprehensive and approachable introduction to the Universal Scalability Law. So you can download that too. Take care.